Hi, my name is Itai Seggev. I'm a senior kernel developer here at Wolfram Research, and I'll be talking about the asymptotic relations that we added in version 11.3 of the Wolfram language. I'll be talking about asymptotic relations. So the plan is to introduce 6 asymptotic relations that we added in version 11.3 of the Wolfram language, show some applications, and discuss connections to other parts of the larger asymptotics project. So AsymptoticLessEqual, as we call it, more popularly known as Big O. It was popularized by Paul Bachmann in the 1890s and work on analytic number theory, building on some earlier work. And basically what it says is, at a point x star, f of x is less than or asymptotically less than or equal to g of x if there exists some constant such that the absolute value of f of x is less than that constant times g of x for all x near x star. This captures a notion that in the vicinity of that point, could be infinity, could be 0, could be anywhere in between, could be in the complex plane, that the magnitude of f can't become arbitrarily larger than the magnitude of g. What Bachmann did was he was studying sums or various other number functions on the primes, and he would split them up into 2 parts. I can do this part. I can prove this part is ignorable. So, and he used O for order. So it's order of this, n to the k, whatever. Now it's much more widely known because of Paul Knuth and computer science, where it's used in algorithmic analysis. So some very simple examples. If you have some monomials at 0, then each power makes it asymptotically smaller than the previous one. So x to the k is less than x to the l if if k is greater than. Am I saying this right? I'm sorry. Right. If k is greater than or equal to l, yes, then x to the k is less than x to the l because you're going to 0 faster. And if we look at some plots, then we see, yes, x to the k makes it 0 faster. The order is reversed at infinity because as you go up, you go to infinity, you blow up faster. Here's a sort of cutesy example. So x squared is less than or equal to x squared times sine of 1 over x plus 2. And that plus 2 is pretty important, which is less than x. And if we look at a plot of that, we see y. So x is going down to 0 this way. X squared is going to 0 even faster. And x squared is hugging, x squared times sine of 1 over x plus 2 is hugging x squared as it's wiggling up and down. Okay, so a little later, little o came along. It was introduced by Edmund Landau, not Lev Landau. And so in some fields and regions, these relations are called Bachmann-Landau symbols. And the difference looks very, very similar, but in the great world of quantifiers, which quantifier you use is very important. So rather than there existing a constant, a positive constant c, it has to be for all constant c greater than 0. And this quantified the notion of ignorable. One part was asymptotically less than or equal to. The other part was clearly less than, as determined by this notion, and you could get rid of it. So, well, these first couple of examples look very similar. Polynomials are ordered. Now, notice that x is not asymptotically less 10 to the 5th x as x goes to infinity, even though it's 100,000 times smaller at every single point on the positive reals. It's not asymptotically less because, well, there's a fixed constant. There's a constant offset in the long log plot, or there's a constant ratio, which means for very small c's, you can't make the c arbitrarily small. It's bounded away from 0. Right, so similarly, x squared is not asymptotically less than or equal to x squared sine of 1 over x plus 2, but it is asymptotically less than x. And notice one oddity of this definition. 0 is less than or equal to, 0 is less than 0. Because we have to satisfy this inequality here where we have a less than or equal to for all positive constants. You have 0 is less than or equal to 0 for all c, yay, 0 is less than 0. Okay, and then perhaps the third most famous, maybe possibly even second most famous, although historically later invention is big theta, which was introduced by Knuth in the 70s. And it says now we have two constants, C1 and C2, and whoops, oh no, there it is. C1, so we say C1 f of x, C1 times the magnitude of g of x is less than or equal to f of x, which is less than or equal to C2 of g of x. So basically, you can't get too much bigger or too much smaller than the other guy. An equivalent definition is f is asymptotically equal to g if and only if f is less than or equal to g and g is less than or equal to f. So some examples. Two polynomials are asymptotically equal at infinity if they have the same degree. So I have ax to the n times bx to the k and cx to the n times dx to the l. And I'm going to assume that k and l are smaller than n. And you know that a and c are not 0, so we actually really do, n really is the highest order, and they're asymptotically equal. Here I'm using the alternative definition where I'm saying each one is asymptotically less than or equal to the other one. So here I'm visualizing three pairs of equivalent polynomials, making a log-log plot, and polynomials are sort of nice. They approach a limit at infinity when you take their ratios. That ratio doesn't have to be 1. I mean, it's going to be 5 because I have 5x cubed plus stuff over x cubed. But it approaches some ratio away from 0. Now, here's a more interesting case. So x squared is asymptotically equal to x squared sine of 1 over x plus 2 at 0. That is true. And if we look at the plot of their ratios, it wiggles mercilessly as we get closer and closer to 0. That's okay, because it's bounded away from 0 and it's bounded away from infinity, right? Our constants are basically C1 is 1 and C2 is 3, and they're both positive and less than infinity. If I didn't have that 2 plus, it would no longer be true because I would be hitting 0 infinitely many times. So you wouldn't be able to make that bound. Okay, so some applications. A famous application is the analysis of algorithms. This is an illustration of merge sort. I will assume you either know what a merge sort is or are just amazed by this picture, so it tells you everything you need to know. But the basic idea is you split up, you have a bunch of numbers you want to sort, you split them up into smaller and smaller groups, then you combine the groups back, but when you group them, you put them in an ordered fashion into the destination array. So the time t of n to sort n elements will be the sum of some constant time b to compute the middle, because we're splitting it in the middle, 2 t of n over 2 to sort each half, because it's a recursive algorithm. We split it once, then we sort each half, combine them, and some multiple an of the number of elements to combine the two halves, where a and b are two positive numbers determined by the computer and your compiler and whatever else determines how fast these instructions actually run. So we have this recurrence equation for how long it takes to run for sorting n numbers. Our solve value can solve that for us. And so we get this, and in particular, this formula is going to be asymptotically equal to n log n. So what does this tell us? Well, if you have any algorithm which takes n log n time. It'll take roughly the same amount of time, where roughly is some sociological term, but you can expect scaling similar to n log n for large inputs. On the other hand, if you have a sort that can run in time n, like a radix sort, that's going to be faster for large inputs because n is asymptotically less than n log n. On the other hand, if you were very naive and used the bubble sort, which has runtime n squared, it'll be slower because n log n is asymptotically less than n squared. Another family of applications is convergence testing. So basically, two functions which are asymptotically equal to each other have the same summation and integration properties. So for example, arctan is asymptotically equal to 1 over n at infinity, and it's well known that the sum of 1 over n diverges, which means that the sum of arctan as you sum over the positive integers is not a convergent sum. On the other hand, arctan over x is equal to 1 over x squared at both 1 and infinity, which means that 1 over arctan of x over x is integrable over 1 infinity because 1 over x squared is integrable over 1 to infinity. It's very simple integral to do, in fact, equal to 1. Okay, so I've talked about less, less equal, and equal. So what about greater and greater equal? And I apparently had a misclick here. So the curse of the partial order. So asymptotic less equal is a partial order, unlike your familiar less and less than. While it is true that for any two real numbers, either a is less than or equal to b or b is less than or equal to a, that's not true for any two pairs of functions. You have incomparable functions. So as an example here, f is sine of x and g is 1 over x. And it is neither the case that f is less than or equal to g or g is less than or equal to f. Similarly, if you have that a is less than or equal to b, you can conclude that either a is equal to b or a is less than b. But that also does not hold for asymptotic relations. Here, f is asymptotic is less than or equal to 1, but it is neither less than 1 nor equal to 1 at infinity. So note in particular, this collection of facts means that the negation of f is less than g is not g is less than f. So here I have not asymptotic less of f less than g and asymptotic less of gf. The first one is true, the less is false. And the same thing happens for less equal, which is perhaps more surprising because while the negation of less is not greater, it's greater equal, you might think the negation of less equal is in fact greater equal, but that's not the case for the asymptotic relations. So that means we have two possible conventions for what does f greater than or equal to g mean. Is it not f of, oh, and I have that backwards there. Is it not f is less than or equal to g, or is it the reverse relationship? And the answer is, Hardy and Littlewood used the first one in their work on elliptic functions, and Knuth used the second one in the 1970s. He was actually aware of the first one, and he said, nobody uses it. Let's change the definition of big omega. And so the winner is, well, analytic number theorists continue to do what they do and use Hardy and Littlewood's definition or some friends thereof, because there are actually 4 different omegas in analytic number theory. Knuth's definition is used in CS and related fields, probably some others. So we follow Knuth. Similarly, f is greater than or equal to g means g is less than f. So for completeness, the definitions are exactly parallel. The only difference is we've replaced the less than or equal to with a greater than or equal to in our definition. And again, 0 is greater than or equal to 0. That'll be important. So I've talked about less, equal, equal, greater, equal, and greater. And then there's this sixth guy, asymptotic equivalent, that seems to come out of left field. And I would say that sort of equal, less equal, equal, the way I think about this is equal, less equal, greater equal are sort of one triad that's very popular in computer science. And then you have less, greater, and equivalent, which are a different triad that you need in the approximation of functions. And that's sort of where we're headed. So this also comes from Hardy's work, not the same paper as Big Omega, but a follow-up one. And basically, so here's the definition. F is asymptotically equal to G if the absolute value of the difference between F and G is less than or equal to Cg of X, and for all, so I'll make that, I'll make that bold there, for all constants C greater than 0 and all x near to x star. Now, the basic idea is that the ratio goes to 1. We couldn't define it that way, and it'll be pretty easy to see why. A different equivalent definition is that F minus G is less than F. And roughly, and again, the intuitive notion here is that you're making an approximation with small relative error. Asymptotic equivalence is a stronger condition. It's a finer condition than asymptotic equality. So if you're asymptotically equivalent, then you're also asymptotically equal. They're both equivalence relations. But on the other hand, if you're asymptotically equal does not mean you're asymptotically equivalent. We saw that already. X to the fifth and 5x to the fifth are asymptotically equal, but their ratio most certainly doesn't get close to 1. So examples. One of, I think, the two canonical examples are Stirling's formula for the factorial function. It is asymptotically equivalent to the factorial function, this square root of n times n over e to the n. It is approximating with small relative, not absolute error. In fact, if you calculate the absolute error, it blows up as n goes to infinity. Another famous example is the prime number theorem. Asymptotic equivalent is prime pi and x over log x, the distribution of primes, are asymptotically equivalent. In fact, their ratio goes to 1. And again, this is an approximation in small relative, not absolute error. So a different example, one is asymptotically equivalent to e to the x at 0. Here we have both small relative and absolute error. More on that in a minute. And here relative error makes no sense, but since it's an equivalence relation, 0 had better be equivalent to itself. But you can't take the limit of 0 over 0 as x goes to a, so that's why we needed this more roundabout definition. Right, and I don't think it's an accident that sort of the two canonical examples are number theory examples, given that this idea sort of came out of work by Hardy. So power series, asymptotic scales, and more. And I'm running low on time, but I think I can still do most of this. So let's look at the kth Taylor polynomial or Maclaurin polynomial of e to the x. And just to refresh our memory, there are the first 5. Well, e to the x is asymptotically equivalent to every one of its Taylor polynomials. In fact, that's basically the content of Taylor's theorem, or at least it's a consequence of Taylor's theorem. But there are lots of other polynomials which are asymptotically equivalent to e to the x. So what makes the kth Taylor polynomial better? Well, to see that, we need to compare the difference in the approximation not with respect to e to the x, but with respect to x to the k. And we see that the error is small with respect to x to the k. If we chose some other polynomial, like 1 plus 2x plus 3x squared, well, it's small with respect to 1, equivalently small with respect to e to the x, but it's not small with the absolute error is not small with respect to x or x squared. In fact, the linear Taylor polynomial is the unique linear polynomial that has small error relative to x. That's what makes it the best linear approximation. So I'm running out of time, so I will just mention very quickly that this x to the k is called the power scale, is a notion of an asymptotic scale where you define a bunch of functions. Each one is smaller than the previous one. So the power scale is one of them. Then you have the Laurent scale. If you include the negative ones, it's sometimes called the Laurent scale. Puiseux scale means you have fractional powers, a fixed smallest denominator. And here are a couple of crazy exponential power guys. And where did these come from? Well, just very briefly, we have these new asymptotic solvers, desolve value, asymptotic integrate, and asymptotic solve is coming soon. And they produce answers. Well, what they do is they choose an appropriate asymptotic scale, and then they expand in that scale. And what it means to expand in that scale, if there is an expansion using the scale, there may not be, but if there is one, it's unique. That's what it means to have an asymptotic expansion with respect to this scale. It may not converge, it may not do lots of other things, unlike Taylor series, which are wonderful and uniformly convergent on compact subsets and all that other stuff. But it is a unique notion of ever-increasing approximation. So that's basically my talk. I'd like to thank Devendra, who is a member of our team, and Adam, who's also up here to answer any questions you may have. I wrote a blog post, so those sections which I had to skip in the interest of time, you can see some more details on the blog post. And are there any questions?